So here is our thought experiment. We have a gun, and we're going to fire the bullet into a spiral. When the pellet fired into the spiral tube emerges, which path will it follow? And let's pretend we're in outer space so we don't need to worry about gravity. Path A, path B, or path C? What do you think? Robbie?
Path B.
Why must it be path B? Why can't it be any of the other paths?
Because there's no force acting.
Ah, did you hear him? If you're changing direction, that must mean you're accelerating, and that must mean there has to be an unbalanced force acting on you. There is no force acting on it. It's going to keep going in a straight line. But this is one a lot of people think once you start moving in a circle, you're somehow going to just want to continue moving in a circle once the circle is removed. You're not. Newton's first will kick in. You're going to go in a straight line on a steady speed. Speaking of circles, let's look at vertical circles. A lot of amusement park rides move in vertical circles. A great example of that is a Ferris wheel. Now, Ferris wheels are pretty tame normally, so I'm going to have Ferris wheels go fairly fast just to make it more interesting. A person rides in a Ferris wheel. We all know what a Ferris wheel is. I told you my embarrassing story about a Ferris wheel, yes? Okay. No? Shouldn't? Yes? No? Okay, this one we're going to pause. This one's not going out on YouTube. It's that embarrassing. A person rides on a Ferris wheel, and they're going to sit on a Newton scale that measures normal force. At the bottom of the Ferris wheel, what does the scale read? Explain your answer using principles of physics. Does the scale read exactly mg? Does the scale read more than mg? Or does the scale read less than mg? So first question, if you've been on a Ferris wheel, do you feel lighter, heavier, or the same at the bottom? And if you're not sure, you can replace Ferris wheel with a swing, because that also traces out a circular path at the bottom of the swing. Do you feel heavier, lighter, or the same? Connor?
I think B, because it's sort of the same thing as the elevator question, where in this case accelerating up.
So,
Well, the guy at the bottom is accelerating up because you're always accelerating into the circle.
yes, and this is the key way to solve this. We are going to do a lot of free body diagrams again. We're going to do a free body diagram on the person. But first, before we jump in, we say to ourselves, what path is this person tracing out? What path is this person tracing out? I'm looking for a word that begins with the letter C. A circle. That's the key. So I'm going to ask all of you, what path is this person tracing out? Everybody? So where must he be accelerating? Toward the center. Where must the net winning bigger force be? Toward the? That's the key. If you're moving in a circle, winner now will always point towards the center. What are the forces acting on this person? Get the obvious one. I know you've missed that. Get the obvious one. Gravity. So we would have gravity pointing down. Is this person sinking into their chair like quicksand? Are they flying into the air like Superman? No. So there has to be a force up, but it's not going to be the same size. Instead, we're going to say, what path is this person tracing out? A circle. Where must my net winning force be pointing? Toward the? So there has to be a bigger arrow pointing towards the center. What force is that I've just drawn? Yes. And by the way, as an explanation, there's the explanation right there. You're moving in a circle. The normal force has to be bigger because something's got to be accelerating you in the circle. So on a Ferris wheel, people feel light at the top and heavy at the bottom. We've already done heavy at the bottom. Why would you feel light at the top? Oh, by the way, ready? Who's winning? Who's losing? Let's write an equation over here. Normal force minus mg equals, and here is the big difference, Fc. We're moving in a circle, circular or centripetal force. If you wanted to get the normal force by itself, how would you do that? Simone, if you're at rest, like right now, that's what you're all feeling because you're not moving in a circle. But as soon as you start to move in a circle, you're adding something to the normal force. The normal force got bigger, you're going to feel heavier. Let's do the same analysis now on the top. What are the forces acting on this person on the top? Get the obvious one. What else? Normal force. Which way? I guess it's going to be pointing straight up because in a Ferris wheel, your head is always pointing upwards. But what path is this person tracing out? A circle. So where must the bigger winning force be pointing? Toward the center. So am I going to draw the normal force bigger, smaller, or the same size as mg? Which tells you first quantitatively that, okay, the normal force is going to be smaller, and I've already told you what you think of as your weight, Drake, is actually the normal force. But let's write an equation. Who's winning? mg. Who's losing? Normal force. And now, instead of F net, it's going to be F circular. You're moving in a circle. Let's get the normal force by itself. Julie, we've done this dance before. We've moved two things back and forth at the same time. I'm going to end up with the normal force equaling mg minus the circular force moving you in a circle. Again, Rebecca, right now, all of you are experiencing just plain old that. But if you're moving in a circle in a Ferris wheel, on top of the Ferris wheel, James, gravity is going to have something subtracted from it. You're going to feel lighter at the top because the normal force got smaller. You're going to feel heavier at the bottom because the normal force had to become bigger. In Latin, the word centripetal means towards, pedal, the center, century. So we call this centripetal acceleration. When you're moving in a circle, we call this centripetal force. It's centripetal with a P, not centrifugal with an F. Centrifugal force is, as I told you last day, not a force at all. It's actually just an object's own inertia wanting to keep going in a straight line at a steady speed. But centripetal force, that's the net force that's pushing you into a circle towards the center. So an object moving in a circle has an inwards net force. That means when you go winner minus loser, which way will the winner always be, Nevada? Toward the center. And that's going to help us with our free body diagrams because we're going to know the winner ahead of time. Which way is winning? Towards the middle. Now, I can't say more than that because it's going to depend, Liam, where you are in the circle. Some like to use the following notation. I will. I'll use AC for an inwards centripetal. You can think circular, but I'm going to say centripetal acceleration. I'll use FC for the net centripetal or circular force. So the subscript C means centripetal. Now the convenient thing is circle also begins with a C. So if you want to, Julie, you can just pretend that the C stands for circular, but I'll use the nerdy physics word because that's how I roll. So, in our winner minus loser approach, this is important. The centripetal force will always be the net force. This is so important, I'm going to highlight it. FC will never actually appear on your free body diagram. You will never write a letter F and a C on your free body diagram. The same way as we never wrote an F net on our free body diagram, we labeled all the individual forces, and then when we wrote our winner minus loser equation, the right-hand side, the equals, was F net. Here, the equals will be FC. It won't show up on our diagram. It'll show up in the equation as the vector sum of all the forces in the diagram. In the previous example, the Ferris wheel is a rigid wheel. The top and the bottom of the wheel will always have the same speed. And the circular motion will be uniform. This is not always true. Consider a pendulum. Of course, this is, wow, tied in a knot. Nope, hang on. Sorry for you YouTube watchers at home. I'm bringing out one of my physics toys. Come here. Okay, now I've tangled up this one. Wow. What was that?
When's the YouTube face reveal coming?
When's the YouTube what review?
Face reveal.
Face reveal? Oh,
Yeah.
show them what I look like?
Yeah.
Oh, I got to keep the mystery going. So, if you watch, I'm going to spin this in a vertical circle, and notice at the top and bottom, the speeds are going to be different. Very slightly, but different. It slows down where? At the top, and then once it goes over the top, gravity causes it to accelerate, and it's going fastest on the bottom. So we can analyze it at the bottom pretty easily. We can analyze it at the top pretty easily. I'm never going to ask you to analyze it at a 45-degree angle or at a 90-degree angle, because then the forces don't line up. Lots of tip to tail and yuckiness. We can handle it. Did I just do a big unit where I flogged tip to tail and vectors? Yeah, okay, we've done that. So, example 3 says, write force equations for a pendulum, the little string toy that I was just spinning. First of all, at the top of the loop. Okay, let's do a free body diagram. What are the forces acting? Actually, let's do the bottom first. The bottom is easier to wrap your brain around. What are the forces acting on the bottom? Get the obvious one. Yep. What else? Is it touching a surface? No. Tension. There's a rope involved? Now, here's the question. Am I going to draw tension bigger, smaller, or the same size as mg? What path am I tracing out? A circle. Where must my net winning force be pointing? Toward the? So I know tension has to be bigger than mg. So at the bottom, part B, my equation is going to be winner minus loser equals Fc. What about at the top? What are the forces acting on it? Get the obvious one. mg. What else? Tension, which way? Towards the center. Can you see I have 2 winners, no losers? My equation at the top is going to be winner plus winner equals Fc. Where is the rope most likely to break? At the top or at the bottom? I'll let you think about that. In a vertical circle, then, there can be tangent forces that speed up the object, like gravity when I was doing my little spin with the string toy. But key idea, the net inwards force is always inwards, and you can calculate it by going ma, but in this case, A is going to be v squared over r, or A is going to be 4 pi squared r over the period. Those are the 2 equations I gave you last day for centripetal acceleration. Oh, and in a vertical circle, no horizontal forces to worry about. Yep.
Why is it t squared on our orbit?
Oh, t squared. Thank you. It is t squared. It's 2 pi r over the period for speed, but it's 4 pi squared r over t squared. Thank you. Let's apply some of this. Roller coaster loops are other great examples of vertical circles. What's the difference between a roller coaster loop and a Ferris wheel? The direction that your head is pointing. You know what? The direction of the normal force. Because I think on a roller coaster, the normal force changes direction. On a Ferris wheel, the normal force is always going to be pointing straight up. Well, it says this. A 70-kilogram passenger is moving at 10 meters per second at the top of an upside-down roller coaster. Find the force the seat exerts on the person. What are the forces acting on this person? Get the obvious one. Get the obvious one. Yes. What else? Connor, is there a chair?
Yep.
So is there a surface? Yes. So is there a normal force? This time there is. Which way? Look at the picture. Yep. What path are we tracing out? So who's winning? Anything that is pointing toward the... So what's my equation? mg plus Fn equals Fc. Let's get the normal force by itself, because that's what it wants me to find. It says find the force the seat exerts. I think that's another way, that's code speak for the normal force. So we'll get Fn equals Fc minus mg. Well, Fc is going to be mac minus mg. Now, if you look on your formula sheet in this unit, you have two expressions for the acceleration in a circle. Which one am I going to use in this equation? It depends on what they gave me. What did they give me? The speed. So I'm going to use the expression for acceleration that has speed in it. By the way, when you go to your Playland physics field trip, you'll almost always use the other one, the period, because it's easy to time how long it takes to do the loop. It's much tougher to figure out how fast you're traveling, but measuring the time, you can do that while you're standing in line with a stopwatch or your smartphone, so you'll almost always be using the 4 pi squared r over t squared equation. But here, what's the normal force going to be? M, what's the equation I'm going to plug, the expression I'm going to put in for circular acceleration? I know there's 2. Why v squared over r and not 4 pi squared r over t squared? Because what did they give me? So v squared over r, you all see where that is? Because some of you are like, oh, huh? You need to be looking at your formula sheet during this unit. And then minus mg. What's the mass? 70. 10 squared over, did they give me the radius? Oh, in the picture. 8 minus 70 times 9.8. What's the normal force? $70 times 10 squared divided by 8 minus 70 times 9.8. Do you get 189? Units? Newtons. Does this person at the top of the loop feel heavier or lighter? Well, what's their normal? 70 times 9.8. Okay, they feel lighter. Now, you could increase the speed, and as this got bigger and bigger, especially with that squared, you could go so fast that at the top of the loop, you would actually feel heavier. The only problem is at the bottom of the loop, you'd probably feel so heavy that you'd be breaking bones. And in fact, we'll talk about this a bit later, but roller coaster loops are never designed to be circular. They're designed to be teardrop shaped, because a circular loop would definitely make you all pass out. The very first shoot roller coasters that had a loop, they actually had nurses and ambulances stationed at the bottom because it was a circular loop, and you would regularly get whiplash or get a nosebleed or pass out, and yet people still paid money. That was great fun! We now realize circular loops are bad. Any of you been to Disneyland? So California Screaming, that loop is close to circular. I've been on a bunch of roller coasters, and most of them have a loop shaped, it's called a clothoid loop. It's shaped like a teardrop. That won't put anywhere near the normal force on you of a circular loop. The California Screaming one is close to circular. If you ever go on it while you're in the loop, either try raising your hands up, you'll find it very difficult, or just before the loop, lean forward, tuck your head down, and then in the loop, try straightening up. You won't be able to. Okay? Hashtag nerd trivia. So, oh, hey, good. I knew I'd thought about this. In this example, what would happen to the scale reading, the normal force, how heavy you felt? If the roller coaster moved slower, faster. Well, normal force equals mv squared over r minus mg. Yes? I went from memory. Is that what we wrote on the previous line? Okay. As v decreases, what happens to the normal force? As this number gets smaller, what happens to this answer? Gets smaller. The slower you go through that loop, the lighter you'll feel at the top. In fact, there's a catastrophic point. If you plug in the right V so that it exactly equals mg, you'll feel weightless at the top of the loop. If you go any slower, you'll get a negative answer. Really, that's saying the roller coaster is going to fall off the track. It's not going to make it through the loop. Or if it's clamped onto the track, it's going to get part way up and comes, in real life, swiveling back down. But if you're not clamped onto the track, it's saying you can't make it through the loop. What about as V increases? Yeah. And again, this may be Captain Obvious, but this is why faster roller coasters are more thrilling. The difference in, I told you, all an amusement park ride does, Rebecca, mucks around with the normal force as best it can. So, okay, we can do that if we go faster. If the pendulum of example 3 or the upside-down roller coaster of example 5 were moving at the minimum safe speed, what would that imply about the forces? So we said that tension plus mg equals mv squared over r. Normal force plus mg equals mv squared over r. It's really the same equation. It's just two different forces are what's causing you to move in a circle. Let's look at the tension one. Maybe you can figure this out. So I'm going to try and go at minimum speed, and I want you to watch the rope. Let me see if I can do this here. Okay, hang on. I can slow down. Slow down. What does that imply if I'm going at minimum safe speed about the tension? How big is the tension if I go at exactly minimum safe speed? Sorry, how big? Zero. How big is the normal force if I go at exactly minimum safe speed? Zero. How fast is that? Come in.
Why is everybody so quiet?
So, at the top, tension would equal 0, and so really you'd have this. Hey, can grown-ups and little kids, well, this is a rope swing, I guess. Will it make a difference whether I'm swinging a tiny ball or a massive Olympic hammer on the end of a rope? What is minimum safe speed? Get the V by itself. Turns out V is the square root of GR. What about for a roller coaster? Well, again, minimum safe speed would mean that the normal force was 0. You would feel just like you were about to fall out of your seat because normal force and tension are playing the same role. So again, you would get mg equals mv squared over r. The m's cancel. The minimum safe speed for a roller coaster, Robbie, is the square root of GR. Of course, you would never really design a roller coaster that way. That would be a terrifying ride. And we're ignoring friction. There is some small amount of friction in real life and things like that. But, okay. If I spin a bucket, you've all probably done this as children or maybe as teenagers. If you spin a bucket of water fast enough, you can invert the bucket and not have any fall out. Explain why. Brendan, I saw your lips moving and I heard you murmuring. Yeah, these are good stuff. Great stuff. How many of you have done this? And then how many of you, especially on a hot summer day, have pushed the envelope, tried to go slower and slower and slower to the point of failure, which is still fun because you get, water on me, right? So here's the question. Why? Yeah.
The inertia is great.
Inertia is a measure of mass. I kind of like your explanation, except I don't like saying that mass is I don't like saying kilograms are greater than newtons. I got that just, you know, fingernails on the blackboard to me. So maybe we can do better.
Normal force is bigger than
What?
normal force is bigger
See, what's holding the water in the bucket, as long as the water feels like the bucket is pushing against it, it's going to feel that there is a force holding it in place. So as long as the normal force is bigger than mg, oh, you know what? Let's do a free body diagram. We got normal force, we got mg, well, let's see. We have this. Normal force plus mg equals mv squared over r. I guess the normal force is going to be mv squared over r minus mg. I'm going to disagree with you, Connor. It's not as long as the normal force is bigger than mg. It's as long as which force is bigger than mg? Yeah. It's as long as this is bigger than mg. You'll have a positive answer, and therefore the water will feel like something is pushing against it from the bucket. Okay? So, as long as mv squared over r is greater than mg, we stay dry. Now, r is constant. It's almost always the length of your arm plus the bucket. But what can you change when you're doing this? Which of the variables can... Oh, by the way, does it matter how much water is in the bucket? Nope. It matters in terms of how much, you know, you'll feel the inertia tugging on your arm, so you probably wouldn't want to try this with a 5-gallon bucket. None of you are that strong. But certainly you've all tried this, I hope, and if you haven't, you need to, with like a sand pail bucket or something like that. As long as my v squared over r is bigger than 9.8, I'm fine. That's the tipping point, or the dripping point. How many of you ever gone over a hill at speed and felt your stomach lurch like you were feeling lighter? Okay? Also probably means you're driving too fast. Well, no, not necessarily. Is there... now, again, I didn't grow up in Pitt Meadows or Maple Ridge. In Abbotsford, growing up there, all of us knew of 3 or 4 good hills where the speed limit was about 80 or 70, and there was a hill right there. You could get that good stomach feeling. There's one right near the Fraser Glen Golf Course, for example. I know of one on South Parallel Road. You guys might know of those little things growing up. So here we go. A 72-kilogram student is in a car that's traveling at 28 meters per second on a hill of radius 120 meters. When the car is at the top of the hill, what upward force does the seat exert on the student? What am I really asking you to find? Normal force. Robbie, what path is this car tracing out? Looking for a word that begins with the letter C. CI. CIR. What path is this car? What? Okay, we're going to try this again. Robbie, you with me? Ready? Scene 1, act 1, take 2, and action. Ignore them. They're not laughing at you. They're laughing at me. Honest. Robbie, what path is this car tracing out? So where must the net force be pointing? Toward the... Okay, you ready? Robbie, my friend, what are the forces acting on this car? Get the obvious one. Gravity straight down. Right? You'll notice I already drew it really big because I'm pretty sure it's one of the winners. What else? Robbie, my friend, what else? Which way? Normal force is down? What? How do you know? No. Look up. How do you know? Because it wants you to find the upward force of the seat, which is code speak for normal force. Am I going to draw the normal force, folks, bigger, smaller, or the same size as mg? Okay? So I can already tell you just by that, will this person feel lighter or heavier in their car? They feel lighter than normal, because normally, no pun intended, normal is mg. They're going to feel lighter. This is what you feel when you go over the hill really quick. Okay? What's our equation? Robbie, who's winning? Who's losing? So it's going to be mg, winner, minus loser. And here is the key. Look up, look up, look up, look up. It's going to be MAC, not just MA, MA, circular. The previous ones I wrote FC, but now I'm saying, Joss, if you want to, as a shortcut, go straight to MA, you can, but just make sure you know it's moving in a circle. Which A am I going to use? Well, it depends. Did they give me a speed or did they give me a period? What did they give me in this question? Speed. So it's going to be mg minus fn equals mv squared over r. Robbie, my friend, what's this question wanting me to find?
FN.
Yes. How would I get the fn by itself? What's right in front of the fn, right immediately in front of the fn? Look up. What's right in front of the fn? You know what? We've done this trick before, yeah? Where we've plussed it. Okay. So I think I'm going to get this. The normal force is equal to mg minus mv squared over r. Again, Rebecca, normally you just feel mg. All of you are feeling that right now. We're subtracting from that. Oh yeah, you'll feel lighter. This time the masses don't cancel. By the way, the fact that the masses don't cancel for this type of a thing is why little kids can go on amusement park rides and deal with the sickness so much better than adults can. We feel it more. Okay? The mass cancels in terms of energies and velocities and stuff, but not in terms of puke factor, or whatever physics term you want to go with there. 72 times 9.8 minus 72 times 28 squared divided by 120. By the way, what if I ran these numbers? What if I got a negative answer? What would that mean? Not that I feel heavier. What if I ran these numbers and I got a negative answer? The car is leaving the ground. And now you've just designed a ramp. Most ramps typically have a concave, but you can get air going over a jump like this, right? It's the classic movie chase scene trope where the bad guys are going down, or being chased by the good guys, and they're going over a hilly road, and you see the cars leaving the ground and landing and leaving the ground, and like this. Okay. I don't think we're going to get a negative answer here. I hope not. No, there you go, 235.2. I'll go 235 units, newtons. Okay. How fast would the car need to travel for the student to feel weightless? If you feel weightless, we want the normal force to be 0. So let's take our original equation, which was mg minus normal force equals mv squared over r. And if we want to feel weightless, we're saying no normal force. Oh, what? I get the square root of GR again. So it's going to be the square root of 9.8 times 120 square root of that, and I get 34.3 meters per second. Just for giggles, let's go times by 3.6, about 123 kilometers an hour, which most cars will do. What would happen if the student went faster? Get air, yeah. Any faster, and we will leave the ground. Okay. Is that all right, James? Make sense? Again, what's the key idea, James? If you're moving in a circle, which way is the net force pointing? Toward the? No. If you're moving in a circle, which way is the net force pointing, Drake? Toward the? Okay. Robbie, if you're moving in a circle, which way is the net force pointing? Toward the what? Toward the what? toward the center. And that's why it all depends, James, where you are in the circle. It's not going to be the ground if you're on the bottom of the circle looking up. But I can tell you where the center of a circle is. Raj has a mass of 72 kilograms. He's riding a Ferris wheel. Oh, I like this question. I like this question. I like this question. This is a nice example of an amusement park ride, which you already clued in. I have a fondness for. Question using circular motion. He's riding a Ferris wheel of radius 12 meters, moving at a constant speed. At the top of the Ferris wheel, the bench that he is sitting on applies a normal force of 450 newtons. So he's sitting on a scale in newtons, and he glances at it at the top, and it reads 450. How fast is the Ferris wheel moving? Okay. Any thoughts on how I might want to start this? Free body diagram. What are the forces acting on Raj? Get the obvious one. Why did I draw mg so big? Because I know the winning force is pointing toward the center. What other forces are acting on Raj? Which way? Why is the normal force pointing up at the top when over here the normal force was pointing down at the top? Yeah, so this is, just be careful. You notice whether we're talking about a roller coaster or a Ferris wheel. In a Ferris wheel, your head always points up. Boring. In a roller coaster, your head at the top is typically pointing down. Another great ride to analyze at Playland is the Enterprise. That's the one that starts out as a flat circle and then raises itself up to a vertical circle. Some great physics going on there, too.
When is that go
May 3rd or May 2nd or something like that, or May 5th. It's the first Tuesday of May. So normal force. Ready, Drake? Who's winning? How do you know? Because it's pointing toward the... Who's losing? So my equation is going to be winner minus loser equals MAC. I can't use VF minus VI over T. I can't use my normal acceleration. I'm moving in a circle because this acceleration is due to a changing direction, not a changing speed. I guess we're going to get mg minus fn equals mv squared over r. What does this question want me to find, folks? The v. Okay. I guess times everything by r and divide everything by m. I don't know that the mass cancels here because I don't see an m in the normal force. Is that okay, Kayla? So I think I'm going to get this. V squared equals r over m square root mg minus fn. A little weird, but I can deal with it. Do I know r the radius? Did they give me that? Yes? Did they give me m the mass? Yes? I know m 9.8. Did they give me the normal force? Oh, okay. Plug and chug. What was the radius? I've scrolled down. 12 over 72 bracket 72 times 9.8 minus 450. I think I can type this in one step. It's going to be 12 bracket 72 times 9.8 minus 450, all divided by 72. Do you get... Oh, why, by the way, 42.6 meters per second would be about 170 kilometers per hour, which Ferris wheels don't move at. What do I need to do now? Yeah. Is this right? Yeah, but you got 42.6, yes? Connor figured it out okay? And then square root 6.53? All right. What's B want me to find? Where? Oh, at the bottom, you say. What are the forces acting at the bottom? Get the obvious one. What else? Which way? Inwards. Am I going to draw a normal force bigger, smaller, or the same size as mg? Is that okay, Andy? So my equation now is going to be normal force minus mg equals MAC. Winner minus loser equals MA. Oh, moving in a circle, AC. I guess the normal force is going to be MAC plus mg. Which expression am I going to use for circular acceleration? The 4 pi squared r over t squared or the v squared over r? Oh, because that's what I just found in part A? I'm using my answer from A to find part B? Cool. So it's going to look like this. M, which was 72, times 6.53. I'll use my answer button there on my calculator. Plus 72 times 9.8. A normal force of 1180. That's, sorry, what? Yep. Oh, good gosh, did I botch that, Mr. Duick? You mean I should be going mv squared over r plus mg. I'm sorry, Duncan, I totally botched that. So it's going to be 72 times 6, Mr. Duick, 6.53 squared, all over, what was r, 12, plus 72. I don't know where that last one came from. Wow, that was a brain cramp. 72 times, thankfully I know that v squared, first of all, let's get rid of the answer button. 72 times v squared was 42.6, divided by 12 plus 72 times 9.8. Let's try that again. You get 961.2, 961 newtons. Can a child swing on a swing? Can they ever, let me just see. Oh, good, I'm going to finish. Can a child on a swing ever swing fast enough to completely do a loop over the swing bar? How many of you have tried this one as a child? Okay. Can you? Anybody succeed with a chain swing? Okay. Put your pencils down. I will show you another video in a second, but first, what's your homework? Number 1. Number 2. 4 is good. What happened to number 3? I must have nuked it. 5 is good. So in 5, I'm telling you the maximum tension, find the speed. So get the V by itself. This is when a rope would break because you spun it too fast. 6 is good. 7, good Ferris wheel question. 12. In number 12, I haven't given you the speed or the period. What I have done is given you the frequency. Well, if I've given you the frequency, I've given you the period. Okay? So that's why A says find the period, B find the centripetal speed, and then find the tension,